Hello and welcome to a brand new episode of IEEE Bonus podcast Beyond Conversations. On today's episode, our guest is Satvik Tripathi. Satvik is currently pursuing an undergraduate degree in computer science from Drexel University in the United States of America. His main areas of concentration are artificial intelligence, mathematics, psychology, and neuroscience. He's also working as a research assistant in Harvard Medical School and Penn Medicine. He has received undergraduate research funds from his university. On today's episode, he speaks very passionately about his research projects, the most fascinating and latest trends in AI in medicine. Hello, Satvik. It's really great to have you on our show today.
It's great being here.
How are you today?
I'm good. I'm good.
Okay, so you're working in two very contrasting fields. One is artificial intelligence, which deals with computer science and mathematics, and the other is medicine, which primarily deals with biology. So, how do you find the sweet spot between these two fields? And what is AI in medicine?
Okay. I'll go talking about the last question first, which is what is AI in medicine,
Right.
and then answering how I found this sweet spot. So AI in medicine is a really cool intersection. As you know, AI is an upcoming technology and upcoming science.
Mm-hmm.
In the past decade has been applied to so many of the problems across the world with from face recognition to object recognition to applications in self-driving cars. While healthcare key, remains a key important place where AI needs to be deployed.
Mm-hmm.
So we use AI for a lot of diagnostic, prognostic, prediction modeling. We do a
Mm-hmm.
lot of with the new models coming in, such as like generative models. We are also being able to generate textual information using, NLP techniques to generate text from images. So basically, creating sort of like a radiology report. Um, and there is just insane amount of stuff that is being done with AI in medicine in general. So there's like a huge spectrum starting from bioinformatics, which deals with more on the cellular or more biological and genetics end, to
Mm-hmm.
so from cellular biology and genetics, there's a whole spectrum to clinical decision making and radiology and just electronic health records and a lot of different stuff that we use here at the hospital and the data we collect from the patients. So that's basically what AI in medicine is. We are using all of this huge big data, which the healthcare systems have, and try to apply AI techniques to find out some patterns and stuff like that for the betterment of the patients.
Mm-hmm.
And going back to your first question, how I found this sweet spot is that I attended this conference at Stanford. It's called the Stanford AMI conference, which is hosted by the biggest center of AI and medical imaging, AMI.
Right.
And that's where I got to learn about all of this. And I was like, wow, this looks fascinating. So that's where the journey started. Yeah. So it's been uh 4 years now. I've been
Mm-hmm.
working in the field. Yeah.
So you're a sophomore at Drexel University, and
Right.
by now you've already published a myriad of research papers. You've already had two publications of book chapters. You're also working with UPenn Medicine and Harvard Medical School. So
Yeah.
that's a really phenomenal body of work at such a young age. Can you tell us about your journey and how did you find this passion in AI and medicine?
Right. Yeah. So as I said, I was growing up, I was a huge Marvel fan, so Jarvis was my first inspiration for sure. So that's how I came in the field of AI. I started taking a bunch of AI classes, starting with
Mm-hmm.
Percy Liang's on
Mm-hmm.
YouTube. then followed by Andrew Ings and like Christopher Manning and all the Stanford professors who teach the AI, ML, and NLP classes. And then slowly I just came into this field of medicine and started working in it. And
Right.
did my first internship at Neosoma, which is a segmentation company which works in clinical glioblastoma, which is brain tumors. I did brain tumor segmentation. That was my first internship. And then slowly from there, I just started working at the labs here at Drexel and slowly migrated to different labs at Penn. And then, I got this fellowship at Harvard Medical School. So that's how I got into the Department of Biomedical Informatics there. So that's been the journey.
Okay. Can you tell us about your most recent research grant at Drexel University?
The most recent one is the one I got 2 weeks ago. Um, so I think you're talking about the one I got last year.
Yeah. So
Yes,
you
it
can
was.
tell us about both.
Yes, I got the grant again. So this year I'll be working on diabetic retinopathy images
Mhm.
for people with diabetic retinopathy. So I saw there's a common um this is like a common trend I saw in the literature that the accuracy amongst classification scores for
Mhm.
multi classification is strikingly low as she compared when you're just doing a binary classification between yes DR and no DR.
Mhm.
Um, so yeah, that's what I'm trying to do here this year, trying to use some sparse coding techniques to basic sparse coding is basically a technique we use at our lab, which is
Mhm.
it's a deep learning technique inspired from our visual cortex. So what we do is we reconstruct the image and then subtract it and try to find a loss. So
Right.
really similar to how the brain works, right? So that's what I'm
Right.
trying to do here with my this project is trying to apply sparse coding on these images and try to reconstruct those nerve and the vessels and like see how it goes for a multi-class classification. So that's the goal for this one. Let's see how it goes. Last year I did this project that I really wanted to do for a long time,
Mhm.
which was Turing test based detection of biases in
I see.
medical AI medical I would say applications.
Right.
So basically, what we did is that we made I'm sorry, we made a Turing test
Mhm.
and we modified it. So for those who don't know what Turing test is, it's basically a test proposed by Alan Turing, who is like one of the greatest mathematicians ever to live.
Yes. Yeah.
And he gave this test to identify if there exists a computer or a machine with intelligence that machine should pass Turing test, in which there it's blindfolded, a person is inside whatever
Right.
uh a blinded stuff, and you keep asking it questions, and based on the questions you need to tell whether the person is a computer or not. So the notion is if the machine is intelligent, it would pass all the questions.
Mm-hmm.
But hypothetically, yes, but in real life, so far, no, because that is the area of artificial general intelligence that we haven't achieved yet.
Right.
So that brought in my question of what if we ask the question, is the machine intelligent enough to do what it needs to do? Like, for example, if you put a Tesla car in a Turing test, it's not gonna pass. But if you
Right.
modify the question to, is it good enough? If you compare it to a driver, maybe
Mm-hmm.
yes. So that's what my perspective was. So I designed my study in a similar way where I took a AI machine, a AI system, to do a clinical segmentation task, and then I had a ground truth with actual segmentations, and then I recruited some clinicians to do the same thing, and then compared the results with another clinicians to figure out whether they could figure out if the segmentation is coming from a machine or is coming from a human. The
Right.
idea was to say that even beyond what accuracies us as researcher we predict that, oh, okay, it's getting a 98% accuracy, it's a 99% accuracy. What does it actually mean in a clinical setting, and how close are we to uh, being as close as to a clinician with
Right.
the enormous knowledge and enormous experience the person has,
Right.
and also to address the whole conversation
Mhm.
of having a clinician in the loop with all these AI techniques coming into role. So pretty much that was the whole premise of our study, and we conducted this study, and we are getting close. We are getting close to AI being able to replicate what a clinician
Humans
would
can
do.
do.
Yeah, but at the same time, we have concerns regarding some of the more edge cases and the cases, say, the machine has never saw before, and also potential biases in terms of like the
Mhm.
population. So yeah.
Right. So that brings me to a rather interesting question we had on our list. So, a
Hmm.
lot of practitioners of research and science have been using the applications of technology in medical sciences. But on to reverse engineer on the same question, how do you think the study of neurology or psychology helps in building better AI models?
Right. So I am a neuroscience and a psychology minor. So that is also one of my key areas of interest, is that building what we call is neurosymbolic AI
Hmm.
or neurosymbolic systems.
Right.
And the lab I work at with Dr. Kim at Sparse Coding Lab here at Drexel, this is a key focus, building AI techniques inspired from human brain. And I think there are enormous potentials in terms of like how we're approaching these newer technologies, in terms of like all these new um you know models coming in. I feel like more of the neurosymbolic models or the neuro-inspired models are lesser in demand for like the data. They don't need as much as data, so it really solves the data problem we have. um, Although we are still struggling and not achieving the best accuracy, but I think it's a
Mhm.
good enough accuracy to be using. um, and I believe that in near future this would be a key area of interest for a lot of people in the next 5 years. I know there's the MIT IBM lab, which is already working on it and had made a lot of progress in neurosymbolic systems, where I think they came out with a paper a few years ago about this data set they came out, which called the Cleverer data set, in opposed to the Clever data set by Stanford. And they trained their model, and basically what they were doing is that they were able to predict the physics dynamics and understanding and building a relationship. So basically, the data set was a video data set of objects colliding in that video, like a ball and a sphere and a cube and whatnot. And the
Right.
model was able to predict based off the common sense that if this sphere is coming in at this
Mhm.
speed, it's gonna hit this.
Mhm.
So, based off some really good rule based, I would say, um, computing, I think it was, and having a lot of causal inference in the system, I believe it was a really interesting research, and it reduced the amount of data you needed to train this model by like
Right.
a lot of amounts. So I think that was really cool. So yeah, I think there's a huge implication of neuroscience and psychology in AI. Definitely. I mean, that's where it's all coming from. So yeah,
Yeah, that's really, really interesting.
yeah.
Moving forward to our next question.
Hmm.
So, can you tell us about your research at UPenn based on precision healthcare?
Mm-hmm. Yeah, sure. So here, we work in collaboration. We do a lot of stuff with, I personally do a lot of stuff with cardiothoracic imaging, which is the chest CT or X-rays.
Right.
Um, and I work with Dr. Dako here, and we try to do a lot of multimodal stuff in which
Mhm.
we're trying to combine the patient data, which is like the simple clinical data such as like age, sex, basic clinical stuff, then combined in with their imaging and then combined in with their genomics and then being able to predict some of the key underlying stuff in, say, non-small cell lung cancer. So one of the paper we came out with, we were able to predict the gene mutation using the imaging, which is really cool. So you can tell a patient is, you know, wild type in this particular gene if based on the imaging and the clinical records we have. And that was really cool. And we used a diverse set of cohort in
Mhm.
building this technology. Also, at the Decipher Lab, we have started to work uh, a lot. Um, we use a lot of brain networks basically because
Right.
they use diffusion imaging, so we are able to build um, tractographies and we are able to build a more structural and functional connectivity and understand how the connectivity works in the brain. And based off that, we can work with different cohorts of patients, look at age and sex, how they affect, um, and race, how does that affect into clinical decision making and how each patient is different. So basically, um, a more precise way of learning medicine. So hence the precision medicine. Um,
Okay.
right, yeah. So yeah, actually, our the PI of her lab, she had a major breakthrough in um, Dr. Verma. She did. She discovered this how the male brain is different from female brain, and she had this major breakthrough. She had her paper in PNAS. Um, so yeah, so and the lab been doing some really cool research in terms of that.
Wow, it just gets more and more interesting.
Yeah.
Okay. So, you're working in basically making AI models for medicinal advancement. So, do you have a set process to build these models that you go through commonly for most processes?
Um, I feel like I would rather put it is that my goal is to uh, serve the clinical workflow and
Right.
hence as a sub part of it building AI techniques.
Mm-hmm.
So I rather first try to understand a good clinical problem that we face today and
Right.
then looking at ways to get a data set or some way to, harness
Mm-hmm.
data. And
Right.
then think about what would be the best suitable model here based off the data distribution and how the data looks like because you can't just apply any model to the data. So you need to understand the data, how the distribution is, and how everything is looking like. And then we can apply advanced computing models into that. So yeah, based off that, we are able to find this model and then compare it against the existing literature, which is really important. And then trying to do understand whether it's biased or not, or is it good enough for application to in a clinical workflow. So these are some of the concerns when working if there's a data leakage and stuff like that. But the first and primary concern remains of finding of a good clinical question to ask and see if we can solve it.
Right. So basically, you would first have to find a problem, then analyze the entire data set for it, and then decide what kind of model you want to use on it.
Right.
Okay.
Right. Yeah.
Coming to our next question, What do you think are some challenges that you face while deploying an AI or ML model in medicinal systems?
That's actually a really interesting question, is that when applying or when deploying in a more clinical setting, um, the answer is a lot. There's a lot of concerns. There's a
Right.
lot of concerns in the space of, say, the bias it might hold. Is the model rigorous enough to go through each and every patient?
Mm-hmm.
And do we really trust the prediction the model is giving? And if the model is deployed, do we have a second check on it? Like, is a clinician going to look at it again of the each report? And if
Mm-hmm.
the clinician is looking, what is the need of AI in the first place? Um,
Right.
and then the questions like how it is doing against one set of races against the others because of how the model was trained primarily, and that is a huge bias inherited in the model itself. Um, but this is definitely what I really want to work on in the coming years. Deploying models not only in major hospitals here, but in uh, in countries with low socioeconomic statuses.
Right.
So I know there is this campaign called RadAid, which works towards like deploying these AI systems in Nigeria and other low-income countries, and they're doing a really great job. And hopefully, I get to contribute to it down the line. So yeah, it's a key challenge, and honestly, a key goal for all of the researchers to um, see their technologies being deployed at some company or at some hospital, and it's actually getting used by the patients. But there's a lot of steps to it. Like FDA again, just getting the FDA approval is a major step, and
Right.
it's a process. I would say it's just a huge process.
Process wherein you would have to be testing at every single step.
Right. So yeah, it's just, and then it's also like if you get one case wrong, it's not just a case; it's a patient you're dealing with,
Right.
and one wrong, because most of the places where these models we build is at a critical stage, and you cannot just give a wrong decision there.
Yeah.
So the other way we're trying to incorporate this or major hospital is that having a dashboard where when
Mm-hmm.
you go up to a clinician, the clinician would have a dashboard knowing that if I give this medication, the patient would, his trajectory would look something like this, or have like a pre-insight. So I know there's been like a lot of research in like opioid crisis where they know which patients are more likely to get addicted or in their
Mm-hmm.
family if there are people who could get addicted. Um, I'm not sure exactly whose research this is, but this is at Harvard Medical School. A lot of people have been working on this, on medication and opioid crisis and stuff like that. So, uh, yeah, this is like an initial phase where we're trying to integrate AI with something sort of a dashboard which is given to the clinician for a more of an insight. But it's
Mm-hmm.
still not, AI is still not like a governing authority or a physical role in the hospital so far.
Right. Considering that you still have to achieve an accuracy that is equal to that of clinicians or trained doctors.
Right.
Right. So, coming to our next question, your second book chapter, Fairness and Ethics in AI Based Medical Imaging. Now, the field of medicine has for ages always been a noble practice, and hence there is a defined set of ethics and rules that need to be followed while practicing medicine. However, with AI and modern technologies, we have an infinite arena of possibilities. There's infinite number of directions where technologies can develop. So, what does your book chapter say about the modern problem of not having a defined set of rules in AI which is used in medicine?
Yeah, yeah, that's what the chapter talks about. I first most I explain what are the three most common biases which are prevalent in medicine, in AI-based medical imaging, which is the data collection, um, the trading process, and the way you build your model, and then the cohort of patients who you sample in, and it also depends on if you apply from A geography, you train it on A geography, and then test it out on B geography. It's not going to work.
Right.
So there are so many constraints like these, and I just try to address them all
Hmm.
in the chapter, and then I also try to give out some solutions in terms of like federated learning or like some new upcoming neurosymbolic techniques or coming up self-supervised techniques where try to reduce these biases in different methods. And I believe that's sort of like the future where it holds in AI and medical imaging, and hopefully the same conversation of getting it applied to clinical settings.
Right. You spoke about some of the methods to reduce these biases. Can you elaborate on this point?
Yeah, sure. So, um, as I mentioned before, the neurosymbolic systems is a really powerful tool to reduce these biases because these systems are really powerful in um, picking up the differences. And you can train on smaller cohorts. So, say you don't have a lot of represented population, but you can just train on a smaller number, and these models would still do really, really good.
Yeah.
Another really good example is federated learning, and something that the center at Penn I work with, the Civica Center, they recently did, is that federated learning is that you train the model at different institution. You share your model instead of sharing your data, and
Right.
then your model is trained at different institution, hence a more diverse patient data, and more well-trained model, and you keep doing this to get a better and better model training. And that's something these guys did, and they came out with the biggest data sharing study ever in brain tumors with Dr. Spiros. He is his study. And it's like a revolution in the field of AI and medicine.
Nice. Interesting.
Yeah.
Okay, coming on to our last two questions.
Yeah.
Can you tell us about some resources that you've used to study in all of these fields that you've been working in?
Yeah, sure. So I would say MIT Open Courseware, that's been the key place I've been doing all of my learning. Um, Definitely one of the best lecture series as you can get. You can get all of your content in for from undergraduate to graduate level classes. Everything is there. Secondly, I love studying on Coursera. There's so many good courses you can do. If you don't want to get a certification, you can just audit the course, and then if you want to get a certificate, you can also apply for like a financial aid options that most of the courses have. I personally did a lot of my fundamentals of neuroimaging and my fundamentals of diagnostic radiology from Coursera, and
Right.
also there are like so many good books out there. Um, I started with Pythons for Dummies. That's where I started. So there are a lot of good books also that you could look into. But primarily, I think MIT OpenCourseware and Coursera are like two really good resources.
Okay. Now, considering that AI in medicine is a relatively new field and you're working at the confluence of a lot of different fields, especially like psychology, radiology, programming, can you speak a few words of advice for the next generation of people who want to step into this field?
Yeah, I mean, I feel like one common mistake people do is that actually, uh, one of the professors at MIT, um, Dr. Halabelson. I spoke to him once. I did his interview, and um, he told me this actually. He's also one of the founders of MIT OpenCoursewares.
Okay.
So he told me this that whenever you're studying computer science in
Mm-hmm.
future, always think about computer science and what. Always look for an intersection. And that thing really stayed with me. And then recently I was meeting him uh, over the summer. I was at MIT, and
Mm-hmm.
then he told me that the reason why only few people who get successful in this intersection is that not only they study computer science, but they also try to study as much as they can at the
Mm.
intersection. So
Right.
that's really important in not just in AI and medicine, right? But any intersection or interdisciplinary field you're going into, you should really know what you're doing. You should really know if you're doing AI and medicine, you should really know medicine. Like I come from a computer science background, but I'm trying to learn as much as I can. I try to
Right.
shadow at the hospital. I try to um, sit with clinician and understand the mindset and stuff like that. So just knowing your domain and just knowing what you're working with, what you're dealing with, is
Right.
really important. Just seeing your data as data would not help you. Like you would end up making models that you don't understand, and then there would come the issue of explainability in AI, and then that would be a whole loop, and there's no point. It would
Right.
never get deployed if you can't explain how your model is
Mm.
working. So you really need to understand your data first. You should really understand what you're working towards, and then I think would be useful.
Right. So finding an application wherein you can actually use your knowledge of computer science.
Right. Yeah, that's the goal.
Okay. So that was our last question for this interview. Thank you so much for joining us on our podcast. It really was a very insightful experience.
Thank you so much for calling. It was really fun doing this.
Yes.